In a world with one man versus his own mind and 24 hours, this is a game jam. There's just one problem. His game, Asteroids, totally different this time, is actually not different. Oh man, it's just asteroids. That's kind of a problem. I can't even shoot. That's even worse. Oh my gosh. Okay. It's not different at all. I mean, it uses all this cool stuff, typed arrays, physics. I had all this fun making it, but the players don't care about that at all. What am I going to do? There are only a few hours left before the deadline. Maybe I can, quickly change it? Maybe? All right, what can I do here? All right. Okay, I could try, maybe making the ship huge. All right, I'll try that. Just make the ship huge. Okay, all right. Now I got a big ship. Cool. Yeah, it's the same game. That's really a problem. Okay, asteroids tiny? That'll be hard to hit. That'll be fun. People like hard games, right? Right? Thank you. Oops. Okay. Well, now it's just, this is just bad. So that's just no good. That's no good at all. Okay. What the heck am I going to do? What if you control the asteroids? Yes, I could do this. This is something I could do. This is something that would win. This is awesome. Okay, yes. Awesome, totally cool. Let's do this. Oh, wait. How will I have the time? This is not an easy thing to do. I'm totally changing my game. How's this gonna be possible? Oh, right. Yeah, that's right. I modeled everything as data. Okay, that's awesome. Yeah, right? Right? Okay, cool. Oh, right. What does that mean? Oh, crap, I forgot. Okay. Is that like a database or something? Because databases are pretty fun, right? No, they're not. They're really boring, actually. They're really quite boring. And they're also not a game, you know? In fact, if you, go up to one and hit the action button a few times, you can kind of, capture one, and eventually, but then it corrupts your save game, and you really kind of get screwed over because then your game is gone. So, oh my God, I've devolved into a meme. Sorry. I'm back. Totally back. Okay, all right. So, what are we talking about here? Okay. Well, before we discover what we're talking about, let's talk about how another version of asteroids might have been created, okay? One that uses an object-oriented approach as opposed to this mystical data concept. So, with an object-oriented approach, you'd have your asteroid, your ship, you'd have your bullet, you'd have maybe some other things. They would inherit from each other. That might look like this. On the left is an asteroid, on the right is a bullet. They're very similar. They all inherit from a renderable thing, which inherits from a collidable thing, because things have to atom smash, which renders from a physics entity, which renders from or inherits from a global world thing. Great. The ship is a bit more interesting. The ship might actually inherit from keyboard control, because we don't need to move it around, right? And there's going to be a lot of implementations done in each of these areas of the hierarchy, especially the ship itself, right? We might have an update, and if anyone saw Hunter's talk in the other room, he was talking about update functions. You're going to have that kind of throughout your hierarchy. You're going to have concrete implementations of things, such as draw. It's actually going to be in the ship. Even though something's renderable, it needs to know how to render itself. And shoot, of course, is going to be in the ship as well, because the ship shoots. Great. So if we wanted to refactor our code, because this is great code, right? You can totally tell what's going on here. If we wanted to refactor this fake code to enable controllable asteroids, what would that look like? Well, maybe this. we'd have to physically take our inheritance tree on the left there. We have to take the keyboard-controlled entity, rip it out, and put it into our asteroid entity, as well as just physically copy code, like the handle input, handling like keyboard and stuff, and the shoot function, probably a bunch of other things too. Probably have to handle copying over data properties, and it's pretty hard to know what those are. But they'd all have to be copied or pasted over into the asteroid. That'd be kind of tricky. And of course, keep in mind that the real world is definitely a bit worse. This is a game jam, right? You just write code and you get it done. And that is really messy code. So it would be worse. So pros and cons real quick. You get kind of faked out. All of your logic is local. It appears to be local. All of your logic is in the ship or in the renderable or in the collidable. But really, it's spread out throughout the entire hierarchy, as well as the state. Your position, rotation, shapes, images, things like that are all spread throughout this large object hierarchy, and it's kind of hard to reason about. It's also hard to optimize since you have to deal with these fat objects, which may have different interfaces, and you don't know, it's hard to do that. So you are restricted from making certain types of optimizations. So that's the object-oriented approach. The data-oriented approach, which is what my Asteroids game is actually made out of, has three main tenets. The first is that functions operate on data, not capital O objects. And what I mean by this are, because obviously new object is capital O, it's valid syntax, okay. But what I mean by this is that an object meaning a fat object, something that is inherits from many other objects or has methods attached to it, anything more than just simple data. So we want functions that are relatively pure. There's always going to be more than one of the data that you're operating on. There's always going to be more than one canvas, even though it's a game in the browser. There probably is going to be more than one for double buffering or effects or something. There could even be more than one ship. There could be more than one asteroid. Of course, there's more than one asteroid. And the final tenet is to not inhibit optimization if the developer chooses to do that. And we'll see how in a little bit. Mostly that means batching things up. So this is not perfect. I barely know what I'm talking about. Let's move on. So it all starts with a pocket. And this system, this thing that I wrote it, obviously, but I didn't write it to be a library that you all use. I wrote it to demonstrate these ideas. So just keep that in mind. So it starts with a pocket. And a pocket is just a container, just like your pocket. And it also has a tick method, meaning that every time you want to update the pocket or maybe call something, you're going to call this tick method. It's not really important, but just so you know that it's something that's constantly running. Once we have a pocket, then we can add component types to the pocket. You mean like in React? Maybe? Well, no, not at all, actually. Components in React they don't have a ton of state, but they do have a little bit of state, or they can have state, and they also have methods or functions inside of them. So these are a little bit different. Here's an example of one. This is a rotation component type. It's the definition of what rotation means in terms of data, in terms of properties. It has an angle property and a rate property, and they both default to 0. And if we look, the pocket, when it's told to create one of these, is going to pass in an object, the CMP object, that we then use to attach our properties to. So this is a pattern implying you pass in options, and then you get back some data. There's also on the further slides the shortcut, which is CMP type, just to save typing, but it stands for component type. So in further slides, you'll see that instead. Here's another example of a drag component, meaning something that slows down over time. It's being dragged upon by an external force. There's no functionality here. There's just the data required to implement drag, which is a percentage of velocity kept each frame, or each time we call update. We'll see how it works in a minute, but just notice it's just data. These are just kind of plain objects. Once we have our component types, our definitions, once we have that, we can then request a key from our pocket, because your pocket always has keys, right? Now, a key is simply a collection of component types that will be turned into instances of that component. So in this case, we're requesting a key be made that points at rotation and drag, and we're passing in a default value of rate 0.9 to the rotation. This is important because I said earlier it defaults to 0, so we're overriding that value. The key that we get back is just an ID, and it is a number. It is simply used to index into something else. This is important later, I swear. But it's just an ID. Here's a bigger example. I know the code. It's a lot of code. It's not important to notice all the details here. It's only important to notice that there are several different things in quotes. Those are the component types. And then the thing after it are the options passed into each component. So in this case, there's no options passed into thrust or drag, but rotation has a default value, default rate. So this is actually the ship. This is how the ship is defined in the Asteroids game. We define our points and some other things, which I'll get into more. So once we have our component data and our keys, then we can write systems. And these are going to modify our component data. And here's how that looks like. This is the system, or effectively the functionality, required to apply thrust to something in the game. So first of all, it has a name. It has requirements. These are the types of data that it operates on. And this system will only be invoked if those types of data exist. And finally, what the system does is its action. The system is invoked. It's given a list of keys that have all of these different components. And then finally, also given collections of each component that you can index into. And this is what that looks like. You can see var k equals keys. We're looping through each key, using it to index into the collection of positions, shapes, and rotations. Now, the actual code that does, like in this case, render point shape, and the previous slide was apply thrust, that code is not on these slides, just so you know. It's not like a magical, oh, and suddenly it moves. This is just showing the structure around it, because that stuff's pretty much the same in most games. OK. Here's another example of a system, or sorry, here is the input thrust system, but there's one more little shortcut that I'm going to be using on further slides, and that is that rather than in this previous slide, the system is invoked once, and then you loop through each key manually. In this case, the system is invoked once for each key, and it gives you the data that you want, your position, rotation, thrust. It's just a shortcut. Don't worry too much about it, but I just wanted to point that out. OK. Now, at the beginning of this, we talked about player-controlled asteroids, right? OK, so are we ever going to come back to that? It's like been talking for a while now. Oh, right. So yes, the first step is rotation. We want to take our asteroids and make them rotatable, because the ship can rotate around. That's the first step to moving around. So here's the rotation code. This is it. This is all the code responsible for rotating something. It has a rotation component and a human-controlled 0-1 component. How scientific sounding. And you might be wondering, well, what's up with that? And also, why is there no data being passed in called human-controlled 0-1? And the answer is there isn't one. And this is our last our last part of our Pocket system. And that is that we use labels as anonymous components. These are just ways to label a key as something. This is the definition of an asteroid. It has a position, a shape, a bounding box, and a rotation. It also has an asteroid. It has itself. It just has a name. It just has a name of asteroid. And this is useful because, for example, in the asteroid ship collider code, we only want to talk to asteroids. We only want to deal with the asteroids. And a ship is very similar to an asteroid, actually. The ship also has shape, position, and rotation. So our asteroid tag, or label, is the only thing that makes this system only be invoked for asteroids instead of all of these things. And just the Pocket gives you a little warning. I don't know if you can even see that, but if it doesn't find the component, it just says, hey, I didn't find it. I'm assuming it's a label. hope it's what you meant. Okay. So now back to this rotation. This is our first step in making the asteroids controllable. We have this tag called human-controlled01, or this label. What happens if we just add it to the asteroids? Maybe something awesome? Let's find out. Here's our asteroid down here. Can everyone? Yes, perfect. All right. I will add this in. Save it. Refresh. Hey, that's not working at all. What happened? What happened? Well, what happened is that we have our human-controlled 01. That's great. What didn't happen is that if we look at the system itself, it accepts a rotation, and it uses the rate to increase the angle of rotation. The logic here is not that important. What is important is that this component, rotation, has a default value of 0 for the rate. So on our asteroid, we need to make sure that instead of just using the defaults, we use an actual value. So here's what that looks like. Here's our rotation. Save. Refresh. We've got asteroids moving around. I swear they're moving around, but hold on a sec. Let me undo my changes from before, those really boring changes. Asteroids are moving. All right. All right, cool. So there's step one. Okay. Yes. Now let's make them thrust. So to make them thrust, here's our thrusting code. We look at its requirements. It has a position, rotation, thrust, and human-controlled 01. We already have human-controlled 01. Looks like all we need is thrust. So here's what thrust looks like in the ship. Let's add it to the asteroid. Here's our asteroid over here. And refresh. OK, we're spinning, and we're moving. OK. Yes. We have a cloud of asteroids. OK. We're really getting somewhere now. Let's make them shoot. OK, so if we look at the asteroid, all we need to do is add this projectile launcher thing, which is it's already on the ship. So let's just add this into the asteroid. This should be pretty good. Let's see, projectile launcher, and the value was launch force. That's how much power how fast it goes. Hit refresh. Oh yeah, look at that. I've got so many asteroids just shooting now, and they even kill themselves. Look. Oh, I can't even. There we go. Yeah, just killing themselves. It's not even a challenge anymore for the ship. He's just like, yeah. All right. That's cool. But now let's make the ship get hit, right? Let's reverse things here. So this is the code that is responsible, minus the actual code, but this is the system that's responsible for colliding asteroids and the projectiles, okay? The only thing that is specific to asteroids about this system, aside from the name, which doesn't really mean anything, it's just some string, is the asteroid label. And remember that we just added that asteroid label to the asteroid for the heck of it, so that we could do things like this. So what happens if we take this system, and instead of telling it to operate on asteroids, we tell it to operate on ships? OK, let's try that. So here's our projectile collider. Going to change this to ship. Keep in mind, if we go back to ship real quick, it has a ship tag, or a label. Hit refresh. And now, if we chase, there we go. It killed itself. But if we chase the ship, eventually, where'd it go? Eventually, if it hits, OK. I should have made the ship bigger. So you can see that the bullets are not being hit by the projectiles anymore, or the asteroids, but the ship, yeah, oh. Go get it. OK, trust me, it dies. Oh. OK, all right, I'm going to do it for real now. All right, here we go. Wait, here we go, for real. OK. It will be impossible to miss, right? Ah, Yeah, OK, got it. OK, the hunter has become the hunted now. The asteroids finally have their revenge. OK. Then there's still tons more work to do. Tons more to do. But not today, because there's just limited time in this talk. You know, we could finish up this thing. So, talking about the data-oriented approach and some pros and cons. These are kind of the same thing. I call them pro-cons because sometimes they're beneficial, sometimes they're not. One, logic is spread out. You have many systems. Your logic is in each system, and it can be kind of tricky to have them all spread out because it's all these separate systems, but it's also kind of nice because they are separated. Your state is completely consolidated. You have components that the systems operate upon, and the only thing that changes are those components. Because we can create a system that operates on a whole range of components, it's a little bit easier to optimize. If we wanted to make all of our positions backed by a typed array for fast integer math, we could do that because all of our positions are actually stored in the same kind of area, or same data. And as you just saw, it's extremely modular. We could take labels, we could take code and just kind of move them around and get totally different functionality. Well, pretty different functionality. So I did mention databases quite a long time ago. So what does that mean? Well, there's actually a pretty good one-to-one analog between what I've done here and the concepts of a database, or at least at a fuzzy level, let's just say. So our component types, our definitions, are roughly equivalent to tables. It's like a schema. We define a table. Each property is a column in that table, such as our position or our rotation has a rate and angle. Those are just like columns in a table. Our components are like the individual entries in the table. They're the rows. Each individual instance of rotation is just a row in the rotation table. Our keys are primary keys. That's why they're called key. Also, the pocket. Come on, that ended up being pretty good, I think. And then finally, our systems are like stored. No, they're not like stored procedures at all. They're more like queries and business logic kind of mixed together, which is like PHP land or something. But it's okay, because it's game development. It's fine. All right. And just to show you how much like a database this really is, if we here's our pocket instance, our container of things. If we look at all the different components in it and just log that out, just stringify and log it out, we get this. It gets interesting if we kind of scroll down to the positions. This is the position for key number 4. This is like entity number 4 or thing number 4. Our values are right there. This was a snapshot in time. When this snapshot was taken, when we stringified this, the x and y values were 719 and 397. So it's like an instant save state almost. And with just a little bit of tweaking, you could actually have save states with this. It's not too hard. Another example is rotation. Here's the rotation for key number 4. It didn't actually have an angle set, but it did have a rate. Yay. OK, cool. I'm sure you're all wondering, did I actually finish the game jam, right? That's probably the #1 question on your minds right now. And get ready. I hope you're prepared. I didn't. There wasn't even a jam. It was just for this talk. I'm sorry if I confused anyone. I'm sorry if you feel gypped. But that's all it was. There was no game jam. And, I hope that's OK. Thank you very much.